In this session, we're going to be looking at shortest path algorithms. In the last lesson, we looked at how graphs could be used as data structure or a data point in itself. And today we're going to be using graphs to do some path finding. The algorithm we're going to be looking at in depth today is called Dijkstra's algorithm, and it's one of the most common ways to perform searches on a graph. A graph could be created for an entire network. It could be created for a set of cities, a road network, a train network, you name it. And then we could traverse that graph using Dijkstra's algorithm to find the shortest path between 2 points. But before we begin, let's check your prior knowledge. Do you remember what the purpose of a graph is? Do you remember how a graph is structured? Would you be able to tell what a node or a vertex on a graph looks like? And what is meant by an edge? Now, if you can answer all of these questions, you're ready to continue with this particular lesson. If there are some gaps, then my suggestion is you should go and revisit the graph lesson before continuing. Okay, let's jump straight into Dijkstra's algorithm. It's pronounced Dijkstra, and on the top right-hand corner, you'll probably see an example of how a graph looks like. Now, Dijkstra's algorithm is a method of finding the shortest path between 2 points on a graph. Each node has a final value and a working value. And the working value is basically calculated by adding the final value of the previous node plus whatever the edge value is. And you keep on calculating these working values because eventually you'll probably find the shortest value. And once you find that shortest value, that becomes the final value of a node. For example, there might be 2 ways of getting to a node, one that takes 3 steps, the other takes 5 steps, and then eventually you'll probably find that, okay, the 3 steps is the shortest, so that becomes the final value of that node. We'll look at all of that in a worked example in a moment. Let's just get through the algorithm. So we start by giving the start node a final value of 0. You're already there. You don't need to do anything to get there. And we give it a label of 1 because that's our first node. Then we give each node connected to the start node a working value, which is based on the distance between them plus the final value of the first node. We check if the working value of the node is always the smallest value as you proceed through the graph. The smallest value becomes the final value and the label gets updated to 2, 3, 4. Basically, we're going through each of these nodes step by step. And we keep on repeating steps 2 and 3 for each node until every node has a final value. Then we trace the route from the start to the end node using the final values to find the shortest path. So that's basically what the algorithm is. But it'll actually make more sense once we get through a worked example. So on screen, you will now see a graph and you need to work out the shortest path between A and G. So let's take it step by step. The first thing we're going to do is redraw the diagram and replace the circular nodes with a table based on the key. So you've got a node letter, which is from the original diagram. And then we've got the order of labeling. The first one is always going to be 1. Then we've got the final value. The first value is always going to be 0 because you're at node A. And then there's a little space which allows you to do the working values. So our first step is write 1 in the order of labeling and set the final value to 0 for the first node. So once we work the first node out, we then look at the nodes connected to it. So in this case, B and C are connected to A, and we then work out the working values for those 2 nodes by just simply taking the final value for node A, which is 0, and for B, we add 5 because that's the edge value. So 0 plus 5 gives us a working value of 5. We write it in the space. And for C, 0 plus 6 gives us 6. We write that. And that's step 2. Now, since B has the smallest value out of B and C, we give it a label 2 and we set the final value to 5. We then start looking at the working values for D and E because those are connected to B, which is the next smallest value apart from A. 5 plus 4 gives us 9. 5 plus 6 gives us 11. And then, as you can see, we now have 3 nodes, C, E, and D, with working values of 6, 11, and 9. Can you now guess where the third label will go? Hopefully you guessed right, and the third label will indeed go to C, which has the smallest working value. Now once we're at C, we can now work out the paths to E and F. So the working value for E would be 6 plus 7, 13. Well, we already have a working value of 11 there, which is smaller, so we keep the previous working value. And for F, it would be now 6 plus 6, which is 12. So now we've got 3 nodes again, 9, 11, and 12, and you can probably guess that the next node where 4 goes will be node D. So basically we are now repeating the previous steps again and again. So from node D we can go to E and G. 9 plus 3 gives us 12 for E. Since E already has a smaller working value of 11, we discard the 12, and then for G we work out 9 plus 12, the working value for G becomes 21. Now we've got 3 remaining nodes, E, F, and G. E is our next node since it has the smallest working value, so we label it 5, and then from here we recalculate G. 11 plus 6 is 17, so the new working value for G is 17, and 11 plus 5 is 16 for F. Since F already has a smaller value of 12, we ignore the 16. Now you've got 2 remaining nodes, F and G. F is 12, G is 17, so F becomes 6. Now since F is the last remaining node and G is the destination, we just simply label F as 6 and G as 7. The final value for F is 12, and 12 plus 8 gives us 20, but we discard that since there's already a smaller value in the working value part, which is 17. So G is the 7th node with the final value of 17. Once all of the final values are calculated, we can use subtraction to work out the shortest route, or you can just use simple addition to work out to 17. So 5 plus 6 is 11, plus 6 is 17, so that path is pretty straightforward. Another way is to just simply use subtraction, where you look at the final value of G and then you subtract each of the 3 paths. 17 minus 12 doesn't give you the final value of D. 17 minus 8 doesn't give you the final value of F. 17 minus 6 though gives you the final value of E, which is 11. So we get back to E and we do the same thing there. 11 minus 3 doesn't give us 9, 11 minus 5 doesn't give us 12, 11 minus 7 does not give us 6, but 11 minus 6 gives us 5, which is the final value for B. And then when we get to B, we can do the same thing. 5 minus 4 doesn't give us 9, 5 minus 5 though gives us 0, which is the final value for A. So we can use subtraction to work our way backwards to A. That's one way of doing it algorithmically. The alternative is to manually do the addition. You can use either method in the exam, but the subtraction one is probably the most suitable one. It's no fun listening to somebody else do mathematics. Try it for yourself. On screen is a question. Find the shortest path between A and I. Try to use Dijkstra's algorithm to see if you can work out the shortest path. And there could be multiple short paths. That's possible as well. However, the first answer that an algorithm arrives to is accepted. So pause the video and have a go, and then feel free to share your answer with me. Now, there are, of course, problems with Dijkstra. That's why we use other alternative algorithms like the A-star algorithm. As you can see on screen, Dijkstra is considered to be a flood-fill algorithm. That means it goes through most of the nodes before it arrives to a solution. There are better algorithms out there which use a directed approach or a directional approach to get to the solution quickly. Now in the next lesson we'll look at one algorithm which fixes the problem that Dijkstra has, and that is the A-star algorithm. But that's all for now. Hopefully you understand how Dijkstra's algorithm works, and you should be able to process a graph and work your way to identify the shortest route between 2 points. If you do have any questions about this, please do get back to me. Otherwise, I'll see you in the next lesson.